The truth about seismographs and Earth's interior? It's not what you think. Most of us picture a machine that detects earthquakes, like an alarm waiting for the planet to ring. But the real evidence is quieter than that, and far more powerful. A seismometer is an instrument that responds to ground motion, such as displacement, velocity, or acceleration caused by earthquakes, volcanic eruptions, explosions, and other sources. Combine that sensor with a timing device and a recording device, and you have a seismograph. Its output once scratched across paper or film. Today, it is usually recorded and processed digitally as a seismogram. That record can help locate and characterize earthquakes. And somehow, the same kind of record can help study the internal structure of Earth. That is the mystery. How does a needle, a clock, and a record of shaking become evidence for a planet no one can open? This is science. I used to think the important part of a seismograph was the dramatic moment, when the ground shakes and the line goes wild. That makes sense. Earthquakes are the events we feel, fear, and remember. But the instrument is not really measuring fear, damage, or even an earthquake directly. It responds to motion of the ground beneath it. That sounds simple until you notice the strange part. The instrument has to detect ground motion while it is sitting on the same ground that moves. The clever part is inertia. When the ground shifts, part of the instrument follows the ground, while a suspended mass tends to resist the motion for a moment. That tiny relative motion gives the instrument something to record. So, the first partial answer is not that seismographs magically see earthquakes. They convert ground motion into a calibrated, measurable signal. And that signal does not care whether the motion began as a quake, a volcanic eruption, or an explosion. The seismometer receives only the consequence at its own site, motion arriving through the ground. That is why one trace by itself is both powerful and incomplete. It tells us that something moved, and it preserves how that motion arrived. But to turn motion into evidence, the instrument needs time. Without timing, a wiggle is just a wiggle. With timing, it becomes a clue. The recording device is where the story changes from motion to memory. Older seismographs recorded on paper or film, leaving a physical trace that could be compared after the shaking stopped. Modern systems record digitally, which makes the same basic evidence easier to store, process, and compare across stations. The seismogram is not the earthquake itself. It is the instrument's record of how shaking arrived at one place at specific times with specific patterns. And here is the first, wait, what moment. One station can give limited clues, but a network of stations is what allows researchers to locate an earthquake reliably by comparing arrival times. If shaking reaches one station before another, that timing difference carries information about distance. Add more stations, and the possible source area tightens. That is how seismographic data helps locate earthquakes, not by seeing the rupture directly, but by comparing arrivals. The same records also help characterize earthquakes. Often, a small nearby event produces a short, sharp record, while a large, distant earthquake can produce longer, more complex arrivals. But the exact pattern also depends on path, depth, rupture process, and instrument response. Explosions can produce patterns analysts compare with natural earthquakes, using arrival times, amplitudes, frequency content, depth estimates, P and S wave behavior, and evidence from multiple monitoring methods. That comparison does not make the instrument a mind reader. It makes it part of an evidence chain: source, wave path, station, clock, record. This production draft also carries a simple process note: LLM JSON parse fallback used. That note belongs in the production record, not inside the geophysics claim. So the instrument is no longer just a detector. It is part of a timing network that turns shaking into evidence. But now the question gets deeper. If these records can locate an earthquake within the Earth, often in the crust or upper mantle, how can they say anything about what lies thousands of kilometers below? Move from the seismograph room to a global map, and the evidence starts to feel almost impossible. One earthquake sends energy through the planet, and stations far away record arrivals at different times. Those arrivals are not random. They carry the history of the path the waves took. This is the operational reveal. The seismogram is not just a local shake report. It is a receipt from a journey through rock. In broad terms, seismic waves travel differently depending on the material they pass through. If a wave moves through one region faster than another, the arrival time shifts. If its path bends, reflects, or weakens, the seismogram changes shape. So the line on the screen contains more than one clue. It contains timing, strength, duration, and pattern. Now imagine the same earthquake recorded at station after station, each one sitting at a different angle from the source. One station catches an early arrival, another catches a later one, and a third records a weaker pattern after the wave has crossed a different route. That spread is not a nuisance. It is the experiment. Each station samples a different version of the same event, as if the planet has run the signal through different filters. No single trace explains the planet, but the differences among the traces begin to draw boundaries around what the interior can be like. When researchers compare records from many stations, they can ask a precise question: what kind of interior would produce these arrivals? This is an inference, not a direct photograph, but it is not guesswork either. The constraint comes from agreement across many records. If the model is wrong, the predicted arrivals drift away from the observed seismograms. If the model improves, the timing and pattern fit better. That is why seismographs matter for Earth's interior. They let scientists test possible interiors against actual wave records. And here is the harder complication around the middle of the story. Earth is not a simple stack of clean shells. Real signals include noise, complex sources, station differences, and paths that sample different parts of the planet. A sensor near traffic, weather, or local vibration can record motion that has nothing to do with the earthquake being studied. A rupture itself can spread through a fault instead of acting like one perfect point source. And a wave may pass through more than one region before it reaches the seismometer, mixing several effects into one trace. So the work is not just reading a line. It is separating signal from clutter, then asking which features repeat across independent records. That is where the instrument becomes a scientific witness. Not because it tells a complete story by itself, because thousands of records can challenge each other. Now shift again from the global map to the inside of the planet. The most important mental shift is this. A seismogram is not a picture of Earth's interior, but it can reject interiors that do not match the waves. That is the revelation hiding in the instrument. The Earth is not opened by drilling all the way through. It is interrogated by waves. The line is the shadow of the interior. That line matters because waves respond to structure. A boundary inside Earth can alter timing or path, and a change in material properties can leave a pattern across many stations. Some waves arrive earlier than a simple model would expect. Some arrive late, weak, or absent in places where a smooth planet would have sent them clearly. Those absences matter because missing energy can be as informative as a strong arrival. When many seismograms share a pattern, the interior explanation becomes harder to dismiss. This is why the same data used to locate and characterize earthquakes can also study deep structure. The earthquake is the source. The seismometer is the responder. The clock is the ruler. And the seismogram is the evidence object. Together, they turn a violent moment into a measurement that can outlive the shaking. And the better the network, timing, and processing become, the more detailed the questions can become. But careful science keeps the claim tied to the evidence. A seismogram does not hand us a perfect map. It gives constraints that researchers compare, refine, and test. That is more interesting than the myth of a machine that simply detects earthquakes. The real machine helps transform Earth's own shaking into a method for investigating Earth itself. There is a quiet humility built into this science. The records are strong evidence, but they are still records made by instruments under real conditions. A station can be noisy. A source can be complex. A path can mix several effects before the signal reaches the sensor. So the best question is not, did one seismograph reveal the inside of Earth? The better question is, what pattern survives across instruments, timings, stations, and events? That is the strength of the method. It does not depend on one dramatic trace. It depends on repeatable relationships between shaking, time, distance, and material response. That also changes how we should imagine uncertainty. Uncertainty is not a failure of the method. It is part of how the method stays honest about what the records can hold. And once you see that, the seismograph becomes something larger than an earthquake recorder. It becomes a way of listening to a closed world. And so we return to the line where we began. At first, it looked like a simple response to disaster. Now, it looks like an evidence trail. Sensor, clock, recorder, seismogram, network, model. A seismometer responds to ground motion, such as displacement, velocity, or acceleration. A seismograph records that response through time. A seismogram preserves the pattern. And many seismograms let researchers ask what kind of Earth could have shaped those waves. That is the real turn. The instrument does not just notice that Earth moved. It helps reveal what Earth is made to do to motion. The memorable line is simple. A seismogram is not the earthquake talking. It is Earth answering back. This seismogram reminds us that evidence is often not a picture of the hidden thing. It is the trace left by an encounter with it. Other invisible structures are still waiting inside signals we already record. On No Science, we follow the evidence, the instruments, and the experiments that change what we think we know. Which would you trust first, the seismographs themselves, or our model of Earth's interior they answer to? Tell us in the comments. Thanks for watching.